So we have finished our last conversation with the topic of the Lewis structures, right? So here's the story about some trends in periodic table. And from the standpoint of, chemistry, that's actually chemistry. So when we say trends, you have to understand that elements in the periodic table are organized in a certain way. You already got the grasp of it, right? So period corresponds to the number of electron orbitals, and group corresponds to the number of valence electrons on the outer shell. Okay. So these two parameters, the number of orbitals and the number of valence electrons on the outer shell, will eventually determine the properties, the chemical properties of the elements to a large extent. And this is why we call it trends in periodic table. So the first trend that I want to chat about is the atomic size. Stephen asked me last class, what's the atomic size and the atomic radius. So it's basically the same. Think about an atom as a ball, okay? Or, as we mentioned on Monday, an onion, okay? With the nucleus being in the center, and the electrons circling around that center on the orbitals. So far, that makes sense? Excellent. So, the distance from the nucleus to the outermost shell will be essentially an atomic radius. Does that make sense? Mm-hmm. And it's basically the same idea as the size. So, the bigger the atom, the bigger its atomic radius. Is that clear?
Can you say that one more time?
The bigger the atom, the bigger the radius.
The radius.
Yes. Now, how does it change within the period and within the group? Let's write it down. So this line represents the period. This line will represent the group, the vertical line. Are you with me?
Yeah.
Let me ask you a very simple question. First question is super simple. As you go in the group from top to bottom, how does the number of electron orbitals, electron levels changes? It increases. In your onion, you have more and more and more layers. Does that make sense?
Yes.
How do you think the size of your onion will change if you add more and more layers? It will become bigger. So essentially atoms become bigger as you go from top of the group to the bottom. Okay? Does that make sense? That's super simple idea. Okay? We're good? Now, how does it change within the period? This is also not complicated, but this time we have to think about the charges. So, take, say, a second period. If you have a periodic table in front of you or near you, look at the periodic table. It's just going to be useful. So, take the second period. What is the number of protons for lithium? 3. What is the number of protons for fluorine? 9. What is the charge for a proton? 1 plus. So the total charge of the nucleus in the lithium atom will be +3. The total charge in the nucleus of the fluorine atom will be +9. Now, this +3 and +9 will attract electrons. Does that make sense? The bigger the charge, the stronger they will attract electrons to themselves. And as they pull electrons on both first and second energy level, they're going to pull them stronger towards the nucleus. Does that make sense to you? They pull them stronger. So think about this. Imagine that in the center of your onion, there's a tiny little fella that pulls on the layers. Bless you. The stronger it pulls the layers towards the center, how does it change the size of your onion, quote unquote? Think about this. This is the guy. It pulls the layers. What happens to the size? Smaller. So, if you go from the left to the right, the size of the atom decreases because of the electrostatic attraction between the positive charges in the nucleus and the electrons that are on the orbitals. Does it make sense? Got it? Cool. Now, this basically shows you the comparison of the sizes. Now, don't take it literally, please. Okay, so it may not be up to scale, but it gives you a pretty good idea that the size of the representative elements, and that's important, representative elements, we are not talking about transitional metals. The size of the representative elements, it decreases from left to right and increases from top to bottom. That idea makes sense? Awesome. Now, next parameter that we need to assess, and it's really important parameter, ionization energy. Can anyone remind me, what is the ion? We talked about ions. An atom. What happened to this atom, though? Ion is atom that either lost something. Huh?
Either lost or gained.
The smallest part.
Okay, hold on. It's a lost or gained what?
Lost or gained a
Electron. Very good. So it's either lost or gained its smallest part. Yes, I didn't realize that you were saying its smallest part. Yes. So it either lost or gained an electron. If atom, now what we're going to be looking here at is the energy that is necessary to rip one electron away from an atom. Does that make sense to you? So how much energy we have to spend to rip the electron, in this example, from the atom of sodium. Does that make sense? Let me ask you this. Yeah, I know I don't know what happened. It's super hot here. Let me ask you this. Do you understand why we actually need to spend energy to get the electron out? Or it requires an explanation? Well, think about this. You have, in the sodium, you have 3 energy levels, right? Does that make sense? On the outer level, outer energy level, the outermost one, there is 1 electron. In order to get it away from sodium, you need to lift it even higher. So you need to get it some energy so it can move on completely away. Does that make sense? The energy that is required to strip the atom from 1 electron from the outermost shell is called an ionization energy. Does that make sense? Does that make sense? Now let's talk about the changes. Let me go back. First, let's talk about the group. Okay? So this picture shows you the change in the size of an atom in the group, and the size increases from top to bottom. Obviously, the outer shell in the atom of rubidium is going to be farther from the nucleus than the outer shell in the atom of lithium. Does that make sense? Mm-hmm. Which atom do you think? Okay. When you're going to spend less energy? Ripping off an electron from rubidium or ripping off an electron from lithium? Rubidium, right? Because the outer shell is so far, nucleus barely holds those electrons. Does that make sense? Just because of the sheer distance. It's so far, there is like very little attraction. Makes sense, right? So, if you don't need to spend a lot of energy to rip it off from rubidium, since it's barely attached, barely fixed, the ionization energy will decrease from top to the bottom of the group. So lithium basically holds on to its electrons much better than rubidium. And that applies to all principal elements, okay? That makes sense? Go ahead.
Is it correct to say that helium has the most ionization energy?
Yes, it is absolutely correct to say. You're absolutely right. For helium, the ionization energy will be the absolutely highest, and we'll see it in a minute. Because next question is, how does the ionization energy change in the period? Well, take a look. In one single period, which atoms are the biggest? On the left or on the right? Biggest on the left, which means they have the lowest ionization energy. You have to spend very little to rip the electrons away. Does that make sense? Okay? You got it? You got it? So ionization energy will increase as you move from left to the right of the period. And it will again decrease if you go from top to the bottom of the group. Am I clear? We're good? So, the last parameter is metallic character. Remember, we divided elements into metals and non-metals. So metals are on the left. Non-metals are on the right. And it turns out that metallic character is basically defined as the ability of an atom to lose electrons. Well, now you know which elements here in this picture have the lowest ionization energy. Left bottom, yes. Rubidium, cesium, they're going to have the lowest ionization energy, and they're going to lose their electrons most easily. Does that make sense?
Yeah.
Which elements will have the highest ionization energy and basically will hold the electrons as good as they can? Stephen said helium. I mean, all noble gases hold them pretty well, okay? But helium will be the toughest. Does that make sense? Now, honestly speaking, bless you, honestly speaking, we aren't that interested in looking at noble gases. Because here's the deal. They can produce chemical compounds. They can produce chemical compounds. But those chemical compounds are really, really exotic. You see what I'm saying? You're not going to work with them. You're not going to encounter them in any of your day-to-day. Believe me. I mean, in my life, I've heard about one. It's xenon hexafluoride. That's it. I just heard about it. We never looked at any others. So they're not really relevant. So if we get rid of noble gases, which elements become the most non-metallic? Fluorine, oxygen, chloride. Does that make sense? So we have to remember that the most metals are here, the non-metals are here. We clear? And there are metals like, transitional properties. Okay? And you will see how this metallic character, how this ability to lose electrons is reflected in the chemical properties of the elements. So this table summarizes what we just mentioned, that the atomic size increases from top to the bottom of the group and decreases as we go from left to right of an individual period. That ionization energy decreases as we go from top to the bottom of the group and increases as we go from left to right of a period. And finally, metallic character increases as we go from top to the bottom and decreases as we go from left to right. So far. Does anyone have you looked at the study guide?
Yes.
I ask this, and I will ask this. And I mentioned it to a couple of you on Monday, and I will say it again. This exam is written off the study guide. If you, nothing is out of the study guide. Does that make sense? Good. So we're gonna chat now, start chatting about the ionic compounds. And
Are you going to post this lecture?
huh?
This afternoon, the lecture wasn't posted correctly. Is it on it now?
No, and I need to. Okay, sorry about that.
Yeah, I haven't seen it.
And I will do it during the break. While this thing is going to be exported, and you're going to be wandering in the hallways. I'm going to post this. For some reason, sometimes I think, yeah, I did that, and I didn't. Sorry about that. So, a huge chunk of what we're going to talk about, we already discussed during the lab portion of the class. Now, what do we need to know? Atoms form ions. Ions become positively charged. Ions become positively charged when they lose electrons. And they become negatively charged when they gain electrons. Does that make sense? Now, how do we call the energy that is necessary to rip the electron off the atom? Ionization energy. That makes sense? So knowing the changes in ionization energy, we can predict whether a particular atom can form a positively or negatively charged ion, easier or harder. Okay. So atoms exchange electrons. And during that exchange, the chemical bonds are formed. And there are two types of chemical bonds that we have to know, two big types. Ionic and covalent. Okay? Now, before we talk about these bonds, I want to ask you another question. What is the maximum number of electrons on the outer electron shell? 8. Forget about helium. We know helium is 2. Nobody cares about helium because the only one with less electrons than helium is hydrogen, and we're going to mention it sometimes. But for our intents and purposes, 8. We good? When atom has 8 electrons on its outer shell, it is most energetically stable. It is, let's call it this way, it's happy. Does that make sense? So each atom sort of tries to make its outer electron shell carrying 8 electrons, so-called octet rule. Octo in Latin means 8. So far, you following me? So how can atom achieve this octet? One way is to become an ion. We're going to be using, as an example, the elements in the first and the seventh representative groups. First, 1A and 7A. So if you would look at your periodic table, and you would look at sodium. Sodium is in the first group, meaning that it has 1 electron on the outer shell. Is that clear? Yeah. Now imagine for a second this electron is gone. What happens to the outer shell? It becomes empty. And you have to understand that shell, outer shell, isn't a physical entity. Do you understand that? It's not a physical entity. It's like a place in the races. You know, like if you participate in the race, first place isn't some place. Like, yeah, they're going to put you on the pedestal, maybe. But it isn't, it's just your position in the race. If nobody takes first place, who's going to get the first place? The second person. Like if the winner is disqualified, who's going to be number 1? The person who got the second place. If second place got disqualified, who's going to take the first place? The third place, you know, the guy that was in third place before. Does that make sense? So when this electron in the outer shell is gone, which shell becomes outermost? The next one, yeah, the second. How many electrons are in the second shell? It's completely filled. 8. Is sodium happy? Yeah. Its lost electron, what's going to be the charge? Positive. It's the sodium ion plus 1, but it's happy because the outer shell is filled. Does that make sense? Let's talk about chlorine. How many electrons does it have in the outer shell? 7. How many electrons does it need to become quote-unquote happy? 1. It gets 1 electron. What's the charge? -1. It's happy, 8 electrons on the outer shell. Does that make sense? Now let me ask you this. Hypothetically, can sodium get 7 electrons on its outer shell? Why not? Probably. Hypothetically, can chlorine lose all 7 from the outer shell? Sure, depends on the energy spending, right? But we'll know it's not going to happen. Because it would be too much energy to strip chlorine of all 7 electrons. Does that make sense? So we usually say, we use the term, and I'm going to operate this term from time to time. The term is electronegativity. It's a very convenient term to use, which basically describes how strong a particular atom attracts, craves for electrons. For instance, think about sodium and chlorine. Which atom will more likely get electrons? Chlorine or sodium? Just chlorine. So chlorine is very electronegative, right? It will just pull electrons towards itself. Does that make sense? Sodium, on the other hand, will lose it easily. And the easier the atom loses electrons, the less its electronegativity. So essentially, if we go back to, sorry, I don't have, let me see. Let me see if I can get something. Okay, hold on a second. Let me switch to this one. Okay, here we go. So this is periodic table. See that? Which atoms will lose electrons most easily? Left bottom, right? So they're least electronegative. Which atoms will crave electrons the most? Seventh group, like top, fluorine, chlorine, right? Fluorine is the most electronegative element. Why noble gases do not crave electrons at all? They're happy. Does that make sense? Okay. So we got this concept. Now let's go back to this one. Did we figure out the ionic bond? So ionic bond is essentially an electrostatic bond, an attractive bond, that is formed between two ions when one atom loses the electron and another atom gains it. Does that make sense? Now, covalent bonds are formed when atoms of non-metals share the electrons. So let me explain. This is metal, say sodium, okay, and the yellow is non-metal, chlorine. When sodium will lose the electron, it will become Na+. When chlorine will gain the electron, it will become Cl-. Does that make sense to you? Mm-hmm. That's ionic bond. You have plus and minus and they attract. Ionic bonds are incredibly strong. So sodium chloride, it's going to be a dumb question. Did you ever touch it? Sodium chloride. It's a salt. Did you ever see, like, not the table salt, but how it looks when it's mined? Because you can mine salt. It's basically it's a mineral. It's a stone. Did you ever try to melt it? No, don't. It has like ridiculously high melting point because the bonds between sodium and chloride are incredibly strong. Does that make sense? This is an example of covalent bond. So you have chlorine and another chlorine. How many electrons each of them have? 7. What they do, they share one of each. So these 2 electrons belong to both chlorines. Okay? That make sense? So how I usually compare the ionic, covalent, and covalent polar bonds. And let me introduce this. So that's in this arrangement when 2 chlorines are sharing the pair of electrons, does any chlorine dominate in this molecule? No. They share it equally. Now let's say you have a molecule of carbon and oxygen. It's carbon monoxide. Those are 2 different atoms. Look at the arrangement. Look at the second period. Which one attracts electrons stronger? Oxygen, because it has 6 electrons in the outer shell and needs only 2 to complete them, right? So it steals this 2 from carbon. Not completely. They still share, but those electrons belong more to which atom? Oxygen. So this bond essentially is slightly polar. Oxygen pulls electrons towards itself. Does that make sense? Kind of. So this is also covalent, but it's covalent polar. What I usually compare these bonds is like kids sharing an Xbox. If you have a really strong kid and a really weak kid, the strong kid will just beat the crap out of the weak kid and take the Xbox. Completely, just take. That's ionic bond. If kids are equally strong, they will share the Xbox equally. So that's covalent nonpolar. Two chlorines. Make sense? If one kid is slightly stronger, they will make an agreement. Let's say one kid plays 5 days a week and another kid plays 2. So that's they still sharing it, but not equally. That's covalent polar. Does that make sense? We're going to talk about these types of bonds as we move on and discuss various types of compounds. Okay? So basically, positive ions are formed by the metals of the first, second, and third representative groups, 1A, 2A, and 3A. Okay? So for instance, again, if you look at the periodic table, you will see calcium. Calcium has 2 electrons on the outer shell. It will lose 2 and become a cation, positively charged ion, with a charge of +2. Does that make sense? Basically, we can say that all alkali metals, elements of the first group, form ions with a charge +1. Always, no exceptions. All alkali earth metals form ions with a charge +2. No exceptions. All representative elements of the group 1A, all alkali metals, always form ions with a charge +1. And the elements of the second group, 2A, alkali earth metals, always form ions with a charge +2. So essentially, when you look at some reaction and it involves, let's say, barium or, I don't know, calcium or magnesium, you look at the group, they belong to the group number 2, they representative elements, it's going to be barium 2+, calcium 2+, magnesium 2+. Is that clear? And when say sodium atom, okay, when they lose 1 electron, okay, they now have same number of electrons on the outer shell as neon has. So they have an electron configuration of the noble gas. Does that make sense? They're perfect. Yes, they're positively charged, but who cares? Okay? Same goes for magnesium in the group 2A. Magnesium has 2 electrons on the outer shell, total of 12 electrons. It loses 2, acquires the same electron configuration as neon, so 8, on the shell that is now the outermost. It's happy. Yes, it has a charge of 2+, but who cares? Does that make sense? Good? Now we mentioned that nonmetals gain electrons. So nonmetals in the group 5, 6, and 7A, they have such high ionization energies that they cannot lose the electrons, they will instead gain them, all right? And let's say chlorine, okay, we're going to, the illustration here is terrible, okay? So that chlorine, as we discussed, has 7 electrons on the outer shell. Has 7. It gains 1 more, gets 8. That makes sense? Perfect electron configuration. Okay. Yeah, same. It has a charge of -1, but who cares? Is that clear? Question? No? We're good? So these are electron configurations and the names for the ions of the first, second, and one of the third group. Nothing particularly interesting. The name of the positively charged ion is the same as the name of the element. So lithium, potassium, sodium, aluminum, calcium, so on. Does that make sense? You should be able, for the first 3 representative groups, you should be able to write down the proper ion. Am I clear? So if I tell you what is the charge on calcium, you have to look at the periodic table. I'm not yet asking to memorize the position. You look at the periodic table, tell me calcium, second group, representative element, the charge of the ion is going to be +2. Clear?
Yeah.
You can expect that kind of a question. Not in the upcoming test though. No, not in the upcoming one.
The one next.
Yeah. Now, what about the nonmetals, the 5th, 6th, and 7th groups? You take the first syllable and you add ide, IDE. So if it's formed by nitrogen, it's going to be what? Nitride. If it's formed by phosphorus, it's going to be phosphide. Okay? If it's formed by sulfur, it's going to be sulfide. If it's formed by...
When you gain the...
When they gain, yes.
And
Yes.
become-
Yes, when they gain electrons and they become negatively charged ions.
And then it will become
So say sulfur and oxygen are elements of which group? Huh? Which group? Number 6. Non-metal, but 6. So how many electrons do they need to become quote-unquote perfect? 2 more. So when they gain 2 more, what's going to be the charge of all this? 2 minus, right? They're going to get 8 total. The charge is going to be 2 minus. So when you have a compound that is sodium sulfide, I'm not putting any subscripts. The charge of sodium always is what? +1. The charge of sulfur is going to be what? -2. How many sodiums do you need to make it electron
2.
neutral? Yes. So that's sodium sulfate. Sorry, sulfide. Okay? Sulfide. Oxygen, oxide. Chlorine, chloride, bromine, bromide, iodine, iodide. Authors of this table very conveniently avoided other elements found in the 6th group, like selenium and tellur. Okay, you don't have to know these elements. The names derived slightly different. So, out of curiosity, for selenium, which is Se, right under sulfur, can you see that? Selenium, name of the anion will be selenide. Not just the first syllable, but the first 2 syllables. So with the naming, if you think chemistry is bad, wait till biology happens, especially microbiology. People who give names, well, but we call them taxonomists, they should burn in hell. Okay? Now, does that make sense? So these are the monoatomic anions that you should be able to name. Does that make sense? So for instance, I may ask you, write down which of the following is sulfide. Well, it's not too hard of a question, isn't it? Or O2 minus is what? Oxide. Does that make sense?
Yeah.
Got it?
We
Cool.
have to memorize all this.
There are 8 of them.
Okay.
That's not much. Some people have more kids than there are monatomic anions.
There's an A here.
Imagine Mormon families, they have like 12 kids. And they have to remember how, unless they number them, they have to remember all the names. Okay? Now, no offense, I have a really good friend who's Mormon. He has only 6.
They have a lifetime to learn.
Yeah? Well, it's not kids. There's no emotional attachment here. So, those are 8 that you need to memorize in terms of monoatomic anions. Names of the ions. Because for metals, come on, there's nothing to memorize. If it's aluminum, that's aluminum. Ion is called the same way as the element is called. We good? Make sense? Cool. So, ionic compounds. We figured that they consist of positive and negative ions. Ionic bonds are extremely strong. Does that make sense? And since they hold ions together very tightly, ionic compounds have high melting points and always are solid at the room temperature. So any compound that everybody knows is sodium chloride. Okay? So you can quite literally take sodium. You can take chlorine gas. That would be a fun experiment. Throw the sodium in the chlorine gas. You should do it in some really good enclosure, because that would lead to a massive explosion right away. Sodium will like burst in flames in chlorine, okay? And the result of it would be sodium chloride, the table salt. It has extremely high melting point, okay? Another example of ionic compound that you may encounter. Do you know Epsom salt? It's magnesium sulfate, as far as I remember. It's definitely sulfate, and I believe it's magnesium sulfate. Okay? Solid, try to melt it. Good luck with that. Okay? Another one that you may encounter, the salt that you put on the driveway in the winter, that's a mixture of calcium chloride and something else. Okay? Solid at the room temperature, super high melting point. Does that make sense? Got it?
When you say super high melting point, means you need
1,000 degrees Celsius.
to
melt it. To melt, now, don't mix up the dilution or dissolving and melting.
Oh, okay.
When you mix sodium chloride and water, sodium chloride dissolves in water.
Yes.
But if you put sodium chloride in the spoon and stick the spoon in a flame, nothing's going to happen. It's going to stay solid. Does that make sense? You need really hot flames to melt it. Look clear? Okay. So, we talked about formulas, so I'll be very short about them. What do you need to remember when you write the formulas of ionic compounds? Charges. That's number 1. I will ask you on the exam for this unit. Not the one that will be on Monday, but for this unit. I will ask you to write down the formulas for ionic compounds. Am I clear? Okay. So remember, it has to be electrically neutral. Now this time, I will not allow you to use the table. So you have to remember, if it's first, you can use periodic table. That's fine with me. But the table with charges, like in your lab book, no.
But you can look at.
Oh yeah, that like, may I borrow it for a second?
Yeah.
Periodic table like this, totally fine.
Oh, that's good.
Totally fine. Okay. So you can look. Say I ask you, write down the formula for rubidium nitride. So you think, okay, rubidium, which group? First A. So what's going to be the charge of a cation? Positive 1. Okay. Nitride, nitrogen, fifth group, negative 3. So it's going to be rubidium 3 nitrogen. Rb3n. Does that make sense? So you can use your periodic table. Is that clear? Huh? That's a lot? That's a lot? Did you take microbiology yet? Well, good luck with that, if you think that's a lot. It's when you have to memorize like 20 different species of gram-negative microorganisms only. Huh? Yeah, it's a lot. It's a lot.
Everything is.
I teach it now. It's 5-week course. Yeah. Yeah. 20 classes. 4 hours a day. Yeah. It's dense. Yeah. So that's a lot. That is an easy write. Okay. So you get the gist. So for instance, we have magnesium chloride. You think, okay, magnesium. Second group loses 2 electrons. The charge is plus 2. Chlorine, 7 electrons, gains 1. The charge is minus 1. So we need 2 chloride anions. Does that make sense? There you have it. Sodium sulfide. Each sodium loses 1 electron, plus 1. Sulfur gains 2, minus 2. To make it electrically neutral, you need 2 sodiums, 1 sulfur. Na2S, sodium sulfide.
I have a question with that. When you say 2, sodium,
Yes.
you put a 2 in front of Na, not a 2 next to the Na. I mean, I'm confused
That's
sometimes.
why it's in front instead of.
And
Hold on a
when
second.
you do this,
Are
when
you talking about this part?
Yeah.
Here, they just
Yeah.
demonstrate the counts. Like 2 sodium ions,
Yes.
1 sulfur ion. When you write down the formula,
How do you
the
write?
convention is always you write down the number of atoms as the subscript after the atom.
Okay, so it's Na and then
2, small 2,
Yes.
S.
Okay.
That's the convention how you write formulas.
Yes.
Because you can't always say, like, imagine you're writing a scientific paper. You can't always write down. And then we produced a compound that contained 2 atoms of sodium and 1 atom of sulfur. That's a lot of words. It's much easier to write down this. And everybody knows. Na2, yes.
Yeah. My question is, are they equal? If you
They
write
just-
it
they just-
this way or that way, are they the same?
No.
No.
No,
they're not.
that's the only way you write. When you write it in English, you don't put period in the beginning of the sentence. You just don't. Just don't. Okay? You put verb after the subject. Usually. It's not important. Okay? Does that make sense? So there are rules. That's the rule. Subscript after the element to which this subscript relates. Am I clear?
Yeah.
Good. So that naming. Name of the metal is always first. general rule of thumb. When you go, let's say, you have a formula, absolutely generic, hypothetical, non-existing compound that contains of elements. Look at this. I'm going to pick the letters that are not in the periodic table. A, L, X. There are no elements that are called A, L, or X. Some hypothetical compound, okay? Does that make sense? You always write the element with the most metallic character on the left. And then metallic character decreases as you go from left to right. Does that make sense? So in this case, here's the deal. Imagine that you have a compound such as sodium chloride. First of all, we call it sodium chloride. Not chloride sodium, sodium chloride. That's a convention. That's the rule. And we write it down as sodium chloride, not the other way around. If we want to write down potassium sulfide, potassium metal will be first. Sulfide, anion, will go second. We clear about that? That's the rule. When we get to bigger compounds like polyatomic anions, like sulfates, nitrates, you will see that rule is followed strictly. On the left is the element with the most metallic character, and on the right, the element with the least metallic character. Does that make sense? Do you want me to throw a curveball at you? Just kind of for a practice. Yes. Hold on.
Saying this would be a later number. It was something positive before you think negative.
Okay. Great rule. Think positive before you think negative. Go ahead. That's the curveball that I was about to throw at you. So imagine that you have a mixed sulfide of two. Do you have a periodic table in front of you? I don't need it. Give it to yourself. A sulfide of two metals, sodium and aluminum at the same time. Which of these two metals has more metallic character? Sodium or aluminum?
Sodium.
They're in the same period, aren't they?
No. The aluminum is in.
They're in the same period. In the third, yeah. They're in the same period. Okay. So aluminum is in the third group, and sodium is in the first. Sodium is more metallic. Does that make sense? So, how are you going to write it down?
When you say group, it's top down.
Yes.
When you say period.
Left to right, yes.
So earlier you say, are they same group? They are not same group.
They're not same group. They're same period. Same period, yeah.
Same period.
So, sodium, lithium, sulfide. Does that make sense? Sodium, not lithium, I'm sorry. I misspoke. I was thinking about some other compound and it just accidentally slipped. Sodium, aluminum, sulfide. We got it? What's the charge on sodium?
+1.
On aluminum? On sulfur? Any subscripts? On what? Why sodium? What's the total positive charge? What's the total positive charge? +1 and +3 gives you?
4.
+4. Does that make sense?
So we need.
You need two sulfurs. That make sense?
Yeah.
Now, let me reassure you. That was a curveball. Curveballs are not for the test. Curveballs to explain how it works, to realize, how we write it down. Does that make sense? Did I answer your question? Good. Okay. So this is just some namings. As I mentioned before, first and second groups and aluminum from the third are the ones that you need to know. It's not much, considering that you have your periodic table in front of you. And names for the 8 elements. Nitride, phosphide, oxide, sulfide, fluoride, chloride, bromide, iodide. That's 8. 2 from the 5th, 2 from the 6th, and 4 from the 7th. Those are the ones that you need to know.
Say that again, 2 from
Okay, so nitrogen and phosphorus from 5th, you can just circle them on the periodic table. It's probably going to be easier. They have a little bit more than I ask. So nitrogen and phosphorus, oxygen and sulfur, and fluorine, chlorine, bromine, and iodine from the 7th. Does that make sense? For those, know the names, and the names are first syllable plus IDE. Yes.
Are all the questions that's on the study guide going to be on the test? It looks like 50.
What? No. Say it one more time.
Are all the questions that's on the study guide going to be on the test?
Of course not.
Huh?
Of course not. Exam or test never intends to ask you each and every question that's on the study guide or anything like that. The purpose of any exam on any subject is to spot check your knowledge. Point is, you never know what's going to be checked. Does that make sense?
Yeah.
So, absolutely not. It's going to be 33 questions, just as usual. But you don't know which 33 there will be, and that kind of the thrill. Okay? What I can promise is that some of the questions, actually, let's say about half, are literally the questions from the study guide. And some of them are basically rephrased, because there are some questions on the study guide that cannot be made into the multiple choice form, so they have to be rephrased. But if you know the answer, you know the answer. Am I clear? So that's your guide for naming compounds. So it goes here, say when you need to name this compound. You first need to identify, you have to think positive before you think negative. So you think positive first, so potassium is cation, oxygen is anion. Potassium is charged positively. It belongs to the first group. The charge will be +1. Oxygen belongs to the 6th group. The charge is -2. So cation is named same as the element, potassium. And anion is named ox, the first syllable, ide, oxide, potassium oxide. Does that make sense? So I can give you a formula and you have to name it. Well, again, multiple choice. Be reasonable. Now, what if you step into uncharted waters and you go into the realm of transitional metals? Metals, they may have various charges. Sounds scary. In this case, you show the Roman numeral that's equal to the charge in the parentheses after the name of the element. For instance, does it terrify you to an extent? Simpler than you think. How many chloride atoms are in this compound? 3. What's the charge in chlorine always? -1. What should be the charge in iron? To make it electrically neutral? +3. That makes sense? So you write down iron and put Roman numeral 3 in parentheses.
How do you know iron is +3?
Because chlorine is always -1.
Yeah.
And the compound, huh?
And there's 3.
And there are 3 chlorines.
Oh,
So it has
okay.
to be electrically neutral.
Oh, okay.
That makes sense? Let's do another one. Manganese O2. What's the charge of oxygen always? -2. So what's the total negative charge here?
4
-4. What should be the charge on manganese?
+4.
+4. So when you write down the name, first of all, what's going to be the name of anion? If it's it's oxygen. Oxide. So you write down manganese. Let me erase this. So since I'm going to write manganese for like another 15 minutes, I will not, but you write down manganese, then you put 4, Roman numeral 4, oxide. Does that make sense? So you let other people know that you're talking about manganese with a charge +4. There is a compound in which manganese has a charge of +2. So you will write down manganese 2 oxide. Does that make sense? We good? Good. That makes sense?
Yeah.
The way you do it. So this is just, now, here, you don't need to memorize anything because it's pointless. Like for chromium here, they show charges of +2 and +3. I can tell you a secret that chromium can have charges +1, +2, +3, +4, +5, +6. And for each of these charges, it can form an oxide. These oxides will have different stability, but they all exist. Does that make sense? Don't memorize, but understand what this Roman numeral means. Let me give you another example. Let's say I kind of not curved, but kind of close to the curved ball. I tell you there's a compound, chromium 3 oxide. So how do we figure it out? So chromium, we keep in mind, okay, 3 oxide. So that 3 means that what's the charge on chromium? 3 plus or minus? 1 oxygen, 2 minus. What should be subscripts?
2 and 3.
Yeah, exactly. 2 and 3. That's chromium 3 oxide. Does that make sense? We're good?
Mm-hmm.
So I will ask you, I will give you a name of a compound. I'm going to use some kind of simpler examples. Okay? Like nickel 2 oxide. What's going to be the formula? Well, if nickel is 2 and oxygen is, if nickel is 2 plus, oxygen is 2 minus, it's just going to be nickel O. Got it? Okay. This is just to give you a variety of numbers. Like for manganese, the favorite story. So manganese here, kind of, well, that's what we're talking about, you know. I'm going to tell you that little story closer to, that's what we're talking about. So fluorine is always -1, right?
Mm-hmm.
So manganese in this compound is going to be 2. So manganese 2 fluoride. Does that make sense?
Yeah.
This kind of gives you the charges. Now, let me be frank with you. This is always this way. This, for monoatomic anions, always this way. So like, if it's nitrogen, it's going to be always -3. Am I clear? This manganese story. In the lab, when you need to make chlorine gas, it's one of the labs in inorganic chemistry course. It's pretty simple. You take a compound that is called magnesium permanganate, and you mix it with hydrochloric acid. I'm not going to write down the reaction, but the result is chlorine gas. It's pretty cool. It's fairly simple to assemble the whole setup. So, I mean, it's doable. Unfortunately, sometimes people make a mistake, and instead of hydrochloric acid, they pour sulfuric acid. When you mix sulfuric acid and potassium permanganate, the product is manganese 7 oxide, which has a chemical formula of manganese 2O7. That's the real compound, which at room temperature, when it is produced, it immediately explodes.
Oh, yeah, because it's not balanced.
Say again?
Because it's not balanced.
Not.
Balanced.
Oh no, it's balanced.
2 and 7.
7 plus. Manganese, in this case, it's 7 plus.
Oh.
That's the form of manganese that has a charge. That's the cation that has 7 plus. It is incredibly unstable, and it explodes at the room temperature. And one of my chemistry teachers told me the story when 2 girls were doing this lab. They mixed up hydrochloric acid and sulfuric acid. And the whole setup exploded. Now, potassium permanganate is purple in color. So she runs to these 2 students, these girls, and they covered in purple spots. And she couldn't figure out if that's blood or potassium permanganate. Turned out to be permanganate. They was fine. But that was pretty terrifying, you know. So, when you see something like this, manganese with, +2, +3, it's the most common ones. But there are many, many other cations that these ones can form. So, this guide here tells you how to do that. So, iron, okay, forms a compound with a chlorine. You see iron, Cl2, okay? You know the charge for chlorine.
-1.
So total number of negatives is 2. How many irons do you need?
2.
So you need the charge of 2 plus on the iron. Does that make sense? So when you name it, you say iron 2 chloride. That make sense?
No.
No. No.
So would it just ask us to name it and we write it out like that?
So what I can do, I can write down the question like, what is the proper name for Cr2O3? You pick one. Does that make sense?
Yeah.
So chromium 1 oxide, chromium 2 oxide, chromium 3 oxide, chromium 3 oxide. I can ask you the reverse. What is the proper name for the following formula? Does that make sense?
Yeah.
What is the charge of a cation in this formula? What is the charge of the anion in this formula? You have to be able to recognize that. Michael? What? Oh, no, that's not the third one. No, not the Monday one. That's the new material. That's not on Monday test. Don't worry about it. Yeah. You good? Yes.
Are there only certain ones with the Roman numerals?
So, that's a really good question. When you write down the names for these elements, you never write down Roman numerals. Because what is the charge of a cation from the first group? Always. +1. Second group, always. +2. Zip. So you know automatically if it's calcium, it has +2. If it's sodium, it has +1. Does that make sense? If you talk about iron or cobalt or nickel or copper, you need to let people know. Are you talking about iron 3, copper 1, cobalt 2? Does that make sense?
Yeah.
Did I answer?
Yes.
Good. Awesome. Okay. Great. Okay. We'll see you in, well, let's be honest, 15 minutes.